As we get ready to start the third part of the used car dealer problem, I realized there was something very important I forgot to say when we were going over the rules for operations on random variables. We can only add expected values and variances if x and y are independent of each other. Okay? If they are independent, then these rules hold. So let's go look at the used car dealer problem and see if that rule holds. So when we go to what is the probability that it will take longer to do the appearance prep than the mechanical checkup? Actually, let's go back and just look at the whole idea. We went ahead and we added the random variables and we used the Pythagorean theorem of statistics, but is that legitimate? So let's think about, does it seem logical that the mechanical checkup part of preparing the used car and the appearance prep, the washing and polishing, are independent? Do they seem to have any relationship to one another? I'm guessing that they're done by completely different groups of people. The cars are, they're working on the cars totally separately from each other, so we're going to assume for the sake of this problem that they are independent. It seems to be a reasonable assumption. So when we go to look at number 3, this is a little trickier. What is the probability that it will take longer to do the appearance prep than the mechanical checkup? And I want to do this a little at a time, so we're going to bring this down a little bit here. Okay, so using our variables, we're saying what is the probability that appearance prep will take longer than mechanical checkup, or what's the probability that A minus M, because look, difference of two random variables, greater than 0. What's the probability that the difference in these two random variables is greater than 0? Now let's think about what are some of the possibilities for those random variables. Okay, so the mechanical checkup takes 90 minutes, but that can vary. It has a standard deviation of 15 minutes. The appearance prep takes an hour on average, and it can vary 5 minutes here and there. Now notice, if these both follow a normal model, 95% of the time we would expect the mechanical checkup to take between 90 minutes plus or minus 2 standard deviations. So it could be as short as 30 minutes or as long as an hour and a half. I'm sorry, as long as 2 hours, because that would be 90 minus 30 or 90 plus 30. So anywhere from an hour to 2 hours 95% of the time. The 60 minutes here, if we add or subtract 2 standard deviations, we're saying 95% of the time it's going to take between 50 and 70 minutes. So yes, it would be possible that the appearance prep time could take longer than the mechanical checkup. Even though the mechanical checkup has an average time that's longer, it also varies more. So the question is, what's the probability that the appearance prep time will take longer than the mechanical checkup? So we have to look at a couple conditions here. First of all, since both appearance prep time and mechanical checkup time both follow a normal model, their difference will also follow a normal model. That's something we learned back in chapter 6. Their sum or their difference would still follow a normal model. We're also assuming that the two processes are independent, because if they aren't, we can't combine their variances. So let's look at what we have here. The expected value of A minus M would be the expected value of A, which, remember, these are times, not costs now, minus the expected value of M, which is negative 30. Now, I could have done it M minus A is greater than 0, too. If you prefer dealing with positive numbers, you can do it that way as well. Now, what's the standard deviation of my model is going to be the square root of 5 squared plus 15 squared. We're dealing with, I'm in minutes now, so rather than using the 1/12 and the 0.25, I'm dealing with minutes. So I'm using this 15.8 minutes. Now, like I always do for my normal model, I want to draw my normal model. So I draw my normal model with a mean of negative 30, and I've got my standard deviation written up here, 15.8 minutes. what I want to know is what's the probability. So this model represents the differences in the two times, okay? Not one time or the other time, but the differences in the two times. So what's the probability that the differences in these two times is greater than 0? Well, I'll put 0 in my model. I'll shave in the area greater than that. I can compute a z-score. You can see with that z-score close to 2, but so we'd expect that to be, if it were 2, we'd expect this to be about 2.5%, so we'd expect that to be a little more than 2.5%. Normal CDF, so here's our 0, infinity, negative 30, 15.8, or if you were using the z-score, you could just do the z-score and then positive infinity. So the probability that a is greater than m, or the probability that a minus m is greater than 0, is equal to the probability that the z-score is greater than 1.898, which is about 2.8%. And of course, we want to write a conclusion statement. So we say, according to the normal model, I can close this now. According to the normal model, there's only a 2.9% chance that the appearance prep will take longer than the mechanical checkup. So it doesn't happen very often. So there's an example of the type of problems that you will encounter when you're dealing with random variables.